In this video, we are going to discuss Jacobian of transformations of Cartesian coordinates to polar coordinates. That is the first item. Later, we need to discuss the Jacobian of transformations from Cartesian coordinates to cylindrical coordinates as a second item. Finally, we can see Jacobian of transformations from Cartesian to spherical polar coordinates. The first item is Jacobian of transformations from Cartesian to polar coordinates. For this, let xy be Cartesian coordinates of the point P. From the point P, we can draw a line PM which is perpendicular to the x-axis. Once you can see that angle XOP is theta, the line OP is R, the distance between point O and P is R. Then r theta are polar coordinates of the point P, where P is xy. Here the distance between O and M is r cos theta, MP is r sin theta. OM is equals to x here, therefore x is equals to r cos theta, MP is equals to y here, you have a y is equals to r sin theta. These are the relation between Cartesian and polar coordinates. To get the Jacobian of transformation, we need 4 partial derivatives. First, differentiate partially with respect to r while theta can be treated as a constant. Dou x by dou r is cos theta since theta is a constant. Dou x by dou theta is negative r sin theta while r is constant. Dou y by dou r is sin theta where theta is constant. Dou y by dou theta while r is constant, you have a r cos theta. Now you can write Jacobian of transformation dou of xy by dou of r theta is the determinant of dou x by dou r, dou x by dou theta. In the second row, we can write dou y by dou r, dou y by dou theta. That is, in the first row we have the elements cos theta minus r sin theta. The second row elements are sin theta, r cos theta. As per the 2 by 2 matrix determinant, A, B, C, D are the elements of the matrix, AD minus BC is the determinant formula. As per the formula, you have r cos square theta plus r sin square theta. The common factor is r, cos square theta plus sin square theta is unity, r times of unity is only r. So that is the Jacobian of transformation from Cartesian to polar coordinates. The next item is the Jacobian of transformations from Cartesian to cylindrical coordinates. Now you can see, let xyz be the Cartesian coordinates of the point P in 3-dimensional space. From the point P, we can draw a line PM which is perpendicular to the xy plane. Join the line OM. From the point M, we can draw a line which is perpendicular to x-axis where the line is MN, and also we can draw a line MS which is perpendicular to the y-axis. So these are important postulates regarding the Jacobian of transformation. Basically, angle NOM is theta here. You can observe here OM is equals to r, the distance between the point O and M is r, then r theta z are cylindrical coordinates of the point P. Here we have ON is x, that is equals to r cos theta, therefore x is equals to r cos theta. OS is y here, the distance between O and S is y here, that is NM also, where NM is r sin theta, therefore y is equals to r sin theta. You can see here the distance between the points M and P is z. Therefore, the relation between Cartesian and cylindrical coordinates are x is equals to r cos theta, y is equals to r sin theta, z equals to z. To get the Jacobian of transformation, we needed 9 partial derivatives of first order. Differentiate partially with respect to r, theta and z, dou x by dou r becomes cos theta while theta is constant. Dou x by dou theta is negative r sin theta while r is constant. Dou x by dou z equal to 0 while r and theta are constants. Dou y by dou r is sin theta while theta is constant. Dou y by dou theta is r cos theta while r is constant. Dou y by dou z becomes 0 while r and theta are constants. Dou z by dou r is 0 while theta and z are, theta is constant, so z also constant. Dou z by dou theta is equals to 0 while r and z are constants. Dou z by dou z is equals to 1 while r and theta are constants. So these are 9 partial derivatives. The Jacobian of transformation is dou of xyz by dou of r theta z. We can present the first row elements as dou x by dou r, dou x by dou theta, dou x by dou z. The second row elements becomes dou y by dou r, dou y by dou theta, dou y by dou z. Third row entries are dou z by dou r, dou z by dou theta, dou z by dou z, and substitute these partial derivatives in row wise as per the third row expansion. For this determinant, you have r cos square theta plus r sin square theta. So r is common factor, cos square theta plus sin square theta goes to 1, r times of 1 becomes r. That is a relation between the Cartesian and cylindrical coordinates, while Jacobian of transformation is only r. Now you can see the Jacobian of transformation from Cartesian coordinates to spherical polar coordinates. It is another important key concept. Let x, y, z be the Cartesian coordinates of the point P in 3-dimensional space. From the point P, we can draw a line PM which is perpendicular to xy plane. Join the points O and M, you get the line OM. From the point M, we can draw a line MN which is perpendicular to x axis, and also you can draw a line MS which is perpendicular to y axis. From this, one can observe that the distance between O and P is r, the angle POZ is theta, angle NOM is phi. So observe these three things: OP is r, angle NOM is phi, angle POZ is theta. Then r theta phi are spherical polar coordinates of the point P, where P is the point lies in the Cartesian system. Here ON is the distance between O and N, that is x, and it is also OM cos phi, that is also expressed as OP sin theta cos phi. OP sin theta, OP is already we have declared as r, it becomes r sin theta cos phi. Similarly, you can see the distance between O and S is the line OS, that is y, and also it is equals to the distance between NM, that is line NM. NM is also expressed as OM sin phi, OM is a line. So OM is also expressed as OP sin theta, where OP is r, it becomes r sin theta sin phi, that is the relation between y and r theta phi. Now you can see Z here, the line MP, the distance between M and P, that is equals to OP cos theta, where OP is r, so Z equals to r cos theta. We have the relation between Cartesian coordinates to spherical polar coordinates as x is r sin theta cos phi, y is r sin theta sin phi, z equals to r cos theta. Differentiate partially with respect to r theta phi, dou x by dou r is sin theta cos phi, dou x by dou theta r cos theta cos phi, dou x by dou phi is negative r sin theta sin phi. The student will be able to remember that when we are going to making partial differentiation to the function with respect to one variable, other variables can be treated them as a constants. Similarly, you need to find dou y by dou r, dou y by dou theta, dou y by dou phi, dou z by dou r, dou z by dou theta, dou z by dou phi. These are 9 entries regarding the Jacobian of transformation from Cartesian to spherical polar coordinates. The Jacobian of transformation is dou of xyz by dou of r theta phi, that is a determinant with the 9 entries. Now we have substituted those partial derivatives in the respective row wise and apply the first row expansion, the last row expansion. The last row expansion gives us this cos theta into this open bracket expression plus r sin theta times of this open bracket expression. The last entry from the third row becomes 0, you need not write it, and simplify this, you will get r square sin theta cos square theta plus r square sin cube theta. Let us take common r square sin theta, you have cos square theta plus sin square theta. Cos square theta plus sin square theta is unity, and you have r square sin theta is the result of a Jacobian of transformation from Cartesian to spherical polar coordinates.